Today, I wanted to look at some procedural generation, a particular algorithm called wave function collapse, but I want to talk about procedural generation and sort of like this whole idea of like complexity arising from almost nothing in general, right? And this is something that you've probably seen in games like Minecraft is a great example where the worlds themselves are procedurally generated, right? But also a lot of like dungeon crawlers. So I'll start out by explaining how Carcassonne works, because it turns out Carcassonne is quite a nice example of this. I'll explain a little bit of the theory behind this algorithm, where it comes from, where the name wave function comes from, its physics. And then I've written a simulation for this so we can see it running in real time and then generate some really big Carcassonne maps by the end of it. And Carcassonne is a board game, obviously. We're working together to build a map, I guess, a country, some sort of kingdom, out of these tiles, and there's like a whole bunch of them here in a big deck. And we get points based on if we can make big cities or if we can make big roads, and this sort of thing. So I'll start, I just need to take a piece. And the rules are basically you can put this anywhere as long as it's touching an existing tile and it sort of completes, or not completes, but lines up with something that's already there, right? So we can join cities together. I could put this here as well, because then it's like grass to grass, but I wouldn't be allowed to put it here.
Oh, because it would stop that road.
It'd stop that road, yeah. Okay. So you'd have to like continue the road. So I'm gonna put this one here.
All right, and can I pick any?
Yeah, any tile.
Okay, let's go with that one. Ooh, bit of
oh
city.
Wow, you've got loads of things there.
So I could do that. Could I do that there?
Could go there, yeah, perfect. Yeah.
All right.
I'll do a few of these. So, and there's also one rule actually that I haven't told you yet, which is when you put one of these things down, you're allowed to claim one of the features, right? So this is, say I'm yellow, this is my meeple, and you put your meeple on the road or the city, and then when this thing is completed, so if the road finishes or if the city finishes, you get the points from this thing.
Okay. So the more of those characters on, the higher the score, is that? Yeah,
exactly. And but then you only have a limited number of these, so you sort of have to prioritize when you're going to put them down and that sort of thing. Okay. Do you want to have another? Go
on then, yeah. Let's pick one, right. So I've got a crossroads.
Crossroads.
But I'm not sure where that's going to go, so I'm going to put it down here. Would that work?
Yeah, that works. So you're allowed to claim one of these roads if you want.
Oh, okay.
So you could be green. May as well do this one. Let's do one more each, and then we can actually get to the point. So
I'm enjoying the game.
It's fun, isn't it? I mean, the box says 35 minutes, so it'd be a long video, but yeah, just two roads here. So I'm actually gonna, I think here I'm forced to either put it here or kind of nowhere interesting. So I'll put it down here. I won't bother claiming that one for now.
All right, and
last one for now.
I'll just go for that one.
Good.
So it could go.
Yeah, you've got a few choices. So you can go upside down. So you could extend this city here and claim it.
Yeah, like that.
Yeah, perfect.
Let's have that one.
And I'll put your meeple on there for you. Mm-hmm. Okay, so yeah, this isn't really what the video is about, but it's a nice example. And well, what I want to talk about actually today is procedural generation. Mm-hmm. So the idea that you can get kind of interesting, complex behavior from simple, kind of small local rules in a lot of systems.
So there's kind of like a link there to our L systems, right? Where you had simple rules, but these kind of plants and things would...
Yeah, exactly that. And actually, there is a link between L systems and what I'm going to talk about today. But what I'm going to talk about today is this algorithm called wave function collapse. Wave functions are a physics term. This is inspired by physics. I'm not a physicist, but I'm gonna do my best to explain where that comes from, but it is just an analogy. But yeah, I've always really liked this algorithm. I think it's really cool. I think I must have first seen it many, many years ago. Someone was using it to generate buildings for some game. You can also use it for generating like textures or images. So actually shout out to Christina who mentioned that, well, yeah, Carcassonne is this, right? So that's what's happening here. So, okay, wave functions. Move this out of the way for a second. So in physics, in quantum physics, we have particles, right? We have like photons, electrons. The weird thing is that these particles can be in multiple states at the same time. And this is literally being in multiple states. So they can be in a number of positions simultaneously. This is called superposition. And then when you actually look at them, when you observe them, they sort of decide where they're going to be, right? It's sort of like a probabilistic thing. Maybe we have some electron, and then this x-axis here is going to be its position, if we're just considering a sort of one-dimensional universe for the time being. And then this y-axis is going to be, well, I'm going to write it as this Greek letter psi of x. You can think of this as the probability that the particle is going to be in this state, i.e. at this position, when we actually come to measure it. And for a simple particle, maybe this would look something like, we sort of have this bell curve type thing, which is it's most likely to appear sort of where it actually is, in the middle of the sort of wave. But then there's a chance that it's going to be kind of miles out, right? It's just a much lower chance. So this is what wave functions are. This is a wave function, and it describes where something will be. And the key thing is that the wave function of two particles can sort of depend on each other, right? So it could be that I have, I don't know, an electron here, E, another one here, E, and somehow they're entangled, and that means that the position maybe of this one, or the momentum of this one, or the spin of this one somehow depends on the spin of this one. The physics reasons behind this I couldn't tell you, but that's maybe the intuition. And that's really as far as I need to go with the physics for now, so I'll put that to the side. This is an algorithm inspired by physics, inspired by this sort of superposition of particles, but it's just an analogy. So this is called the wave function collapse algorithm. And what it does is it's used often on like grids of cells, right? Or kind of maps or connected things where the state of one thing is sort of dependent on the things around it, which is a lot like this. So if I actually bring back our map from earlier, or a part of it, so what I could do is I could say, well, we have cells around this, we just don't know what they are yet. So they're in a superposition, we could say. So I'm going to draw these in, and what we can say is that each of these cells we're sort of thinking of as a quantum particle, in the sense that they are themselves superpositions of all of the possible cells, all the possible tiles that we could place here, and which would line up then with the rest of the map. So this one, for example, because there's a road coming into it from the left, I know that there must be a road here. And actually, same goes for this one. I know there must be a road there. Actually, same for this one. Same for, there's a lot of roads here. And then this one, we have a city on the bottom. And so I can sort of draw in roughly, we know that this one must have a city on the bottom side of it. But everything else is kind of indeterminate at this point. So I draw this like an open box, right? We could have a road here. We also might not have a road here. Actually, I'll fill in these to make them a bit clearer.
Oh, I see.
So all of these paths sort of represent roads, right? But these dark ones represent roads that we know we must have. But these light ones, we could have, we could not have. What the algorithm says that we do is we observe one of these, right? So we look at one of these and we measure it. And to do that, we go through each of the sort of possibilities, right? And we say, okay, what could it be? And we just randomly choose one. And then we can propagate this to the rest of them. So I'm going to pick this cell sort of arbitrarily. And you can see that we have 3 sort of unknown roads here, which means that actually there are, let's see, 2 times 2 times 2 possible tiles that this could be, right? Because each of them could be a road, or could not, or not a road.
Okay,
And so I'm gonna dice here. And so for each one, I'm just gonna roll a dice. And let's say if it's even, then it's gonna be a road, and if it's odd, it's not. So the top one, odd, that means it's not a road. So what I'm going to do is I'm going to draw this in as red, which means we definitely don't have a road there. There's a 4, so now we definitely have a road here. And then finally, a 1 and odd meant we don't have a road. And so what we've done is we've collapsed this cell. You could say that it's no longer in a superposition. And actually what I'm going to do to indicate this is I'm going to find the specific tile from the deck, and I'm just going to put it there. And so this is now in an observed state, right? But the key thing is that all of these cells are kind of entangled with each other.
Yeah, so the one below it, for instance, straight away, we know that that can't be a road.
Yeah, exactly. So this must be no road there. And then in terms of propagating, that's the only one which we currently had. But we also get all of the new possibilities of these cells around it.
Yeah.
So I'll just quickly draw these in. And we could keep on doing this, and we'll sort of get a larger map. And actually, this is quite a lot like playing Carcassonne, the only difference being that when we're playing Carcassonne, we are taking the top tile and we specifically have to play that one. But it's not that different. And you can get like, what happens if you keep playing is you get sort of a big map, something like this, just to give you an idea of what it looks like when we finish. And I thought, well, yeah, it'd be cool to generate a large map or kind of automate playing Carcassonne for us using this algorithm. This does, of course, work with cities as well. Here I'm just really looking at roads. But you can imagine that for each of them, we also have the possibility of like, does it have a city, does it not have a city?
Are there any other features? Is it roads and cities and grass? Basically?
So there are a couple more features. They're less interesting when it comes to wave function collapse, but they're interesting when it comes to winning the game. We have monasteries. We also have another slightly different feature, which is a city with a shield on it. And the shield just says you get, I think it's an extra point if you own this city. So yeah, if we just model roads, cities, or neither, then so that each side has 3 possibilities, right? Each side is either a city or it's a road, or it's nothing, which means that there are 81 possible. So this is 3 times 3 times 3 times 3. That's 81 possible tiles that we could have. Carcassonne only has, I calculated it, 56. If I do this naive sort of each road, each city, yes or no, it's entirely possible that I'm going to end up saying, oh yeah, okay, I have this tile, but I don't actually have that tile.
Yes.
Because it's just like that. So you just got to be careful about that. So yeah, what I've done is I've made a little Python program that simulates this for us, because obviously this takes quite a long time to do by hand. Just to start with, we have a nice simple example where, okay, so here's our board, and we've got the same starting tile, and you can see around it is sort of see these fuzzy tiles, and these are representing the fact that we're in a superposition, right? So it could be any of these, and it's just drawing all of them on top of each other. And so if I do the next step, it's just going to do it for me, and it's picked one. It's picked this one, and it's collapsed it to this, which this purple thing is just one of those shields from earlier. And I can just keep doing this. And what it's doing is exactly what I was doing here. The only difference being where I was just picking a random cell to collapse, this is choosing the cell with the fewest possibilities. Right. The reason being, if we collapse the cell which has the fewest possibilities sooner, then we're going to have less chance of leaving sort of holes behind.
Oh, because there'll be potential problem areas on there that we
can't
do anything.
Yeah, it's exactly that. It's that if we have a cell which only has, say, 1 or 2 possibilities, and we leave that until much later on to actually collapse, chances are when we get there, that's not going to be a possibility anymore, and we're going to get some holes which we don't want because it doesn't look very nice. Okay. So I can actually just have this run all the way. And there we go, we have a finished game of Carcassonne, actually, which really looks a lot smaller than it does in real life when we have it on here. That's all 72 tiles.
Oh, okay.
But yeah, this is pretty cool, right? So we have a big road in the middle, everything's connected up nicely. So this is kind of the basic algorithm, right? The basic algorithm is pretty straightforward, I would say. It essentially boils down to look at a cell, choose a possibility for that cell, and so on and so on and so on. But when we're playing Carcassonne, we're not just randomly making decisions, or some people are maybe, but we would try not to. And so what we can do is that we can actually define our wave function. So remember, the wave function is this function saying, for every cell, what are the possible cells? We can redefine this, and we can also redefine this concept of entropy, which I'll come to in a second. And these are both very simple things, but by slightly changing the definitions, we can get some really interesting behavior here, and also kind of closer to maybe a real game of Carcassonne. I'm going to look at this cell here. I'll circle it in green. So I'm looking at this one. And do you remember the wave function, we write it with this psi symbol? And so we can say that the wave function of, I'll draw a green box for my cell here, is literally just the set of possible tiles that it could be. So we could have the tile where we have a road coming out from the left. And actually, let's just say nothing else here, because we know this red one is not a road, and then we have these two. So that's one option. We could also have the same, but also maybe we have this right-hand road here. And finally, I think finally, there's only 3 options. Is that right?
Well, presumably you could have...
Oh, we could have both of
yes.
them as well. Yes, absolutely. Thank you. Yeah, so we could have that one, and we could have... My laptop's in the way. Exactly. So there would also be the possibility of having a city on there. For now, I'll just consider the roads. Yeah. But the cities, they don't add a whole lot of interest for drawing it. But the computer does the cities, don't worry. So this is our wave function. And what I've said is, of all of the cells, when we collapse one, we want to choose the one that has the fewest possibilities, i.e. the smallest wave function, right? So here we have 4. I think all of the others we have more than that. And the way we know that is that we define this other concept, which it also comes from physics, and also other things. Actually, there are 2 definitions of it, and it's a bit confusing, but entropy, right? Mm. So entropy, and I'm sort of talking about this in the information theory sense. Entropy tells us how surprised would I be if this comes up, or how much information am I going to gain from collapsing this cell, right? Mm-hmm. To make that a bit clearer, I'm going to define entropy, and I'm going to define entropy of, again, it's going to be this green one, and that's going to be the length of its wave function. So it's a pen swapping here. So these bars just mean the length of this set, right? So in this case, it's going to be 4. And so we can kind of rephrase what we said earlier as we're just choosing to collapse the cell with the lowest entropy, except from, of course, the cells which are already collapsed, because these have entropy of 1. So there are a whole lot of different rules in the game which we haven't kind of represented so far. There's also a lot of strategy that we might employ as players of the game, which we have just not at all represented yet. So I'm going to start off with this rule that we're not allowed to just pick any tile we want, right? It has to be the top tile in the deck. And this is really easy to represent, actually, because we just need to redefine this wave function. So we've said before that the wave function of a cell tells us essentially the possibilities of this cell. But actually, we could say that the wave function is a function of not only the cell, but also the deck. And so the second thing here is the top tile on the deck. Let's call this, I'll do another square, but I'll just write top inside it. Actually, an interesting reading of this is the state of all of the cells is entangled with the state of the deck, because that's all entanglement is a wave function where it's a wave function of multiple particles or multiple things at the same time. And what we could say is, call this wave function 2, because it's a different one. We can just define this as this is all of the tiles, so T, all of the tiles T, such that this tile T is in the original wave function for this cell, and t is equal to this top of the deck, right? So all this is saying is, rather than the wave function being everything that could possibly fit there, it's everything that could possibly fit there as long as it's on the top of the deck. And that's all we need, right? You can imagine sort of define the same thing for all of the cells, and we can see what happens in my simulation. As you can see now, we have the deck shown at the bottom, and this leftmost tile here is the top of the deck. So this is the one we have to play. And what you can see is that the possibilities of these two neighboring cells to our starting cell, they must be this one, right? But we know we can't possibly put anything below it. We can't possibly put anything above it. And so we have to play that one. But it could equally be left or right. And so we play it, and then we get a new thing at the top of the deck. This time, actually, it's this red thing. This is representing one of these monasteries from earlier, so this doesn't actually have any roads or anything connected to it. So this must go somewhere where we don't have any roads and we don't have any cities. It's only one option, and so it's going to go there. Here's an interesting one. So we have sort of like a angle road thing, and also an angle city thing, and it happens to have a shield on it. And so this can actually go in 4 different places. In 2 possible ways for each one, right? It can go sort of this way or this way.
The orientation can change.
Yeah, and that's
so it's, yeah, right, okay.
Gives us different possibilities. So we're going to choose randomly. I think they're all going to have the same chance because they're all going to be 2 possibilities for each one. And again, we can just continue this, so on, so on, so on, until our deck runs out. And okay, cool. Well, what can we see here? So firstly, it's a more realistic game. We haven't cheated. But the downside is, of course, we now have, the structure isn't as nice, right? We have a lot of holes, and we have a lot of short roads and things where we didn't quite have the tile that we needed at the time to complete this feature that we were working on. So when we're playing the game, obviously there are lots of things that we might want to do in order to get a higher score, or well, realistically it's that, or make a nicer looking map and that sort of thing. And one of these is that we might want to, if possible, prioritize making a longer road, or extending an existing road, rather than placing our new sort of road tile in just some random space, which is what we kind of got when we had to just take the top one and we randomly put them down. So we've got a lot of disconnected roads and disconnected cities, which is not very nice. So what we can actually do is we can redefine our wave function, these are the possibilities for each tile, in such a way that we are prioritizing this. So one small change we have to make to the wave function is that now, if I say wave function of, for example, this, instead of just a set, we now have kind of like a weight or a probability for each possibility. So I could say this is going to be whatever it might be. So, sorry, that's already a finished tile. But if I were to say maybe it's almost finished, but we might have a thing there, right? This is going to have 2 possibilities. We could completely put all of the roads in, or we could leave the top one blank. I'm going to add some extra information to this, and I'm going to say, okay, maybe this has like a weight of 2, and this has a weight of 5. And then when we come to collapse this cell, we're going to be more likely to choose this one. And what I can do with this is I could say the wave function is going to be higher for a particular option if this is going to continue a road that already exists, or it's going to continue a city that already exists. And I also want it to be higher still if this road is longer than the other ones. And so I can sort of write this like the wave function of, let's say I have a cell here and another cell here. And you can kind of read this as the wave function of these 2 being next to each other. Let's call this like wave function R for roads. And I'm going to take the previous wave function, so that is just the regular old kind of unweighted one. Well, I'm going to multiply each of the items in here by, so the length of the road, if there is one. So length of that plus length of that. So if these things do actually form a road, so like, let's say if there's a road going through them, or it's just going to be one otherwise.
So there's kind of a dependency there, right?
Yeah, exactly that. And you can kind of read this again as an entanglement, or it's sort of, they are now dependent on each other. So whether I have this one and this one is a function of both of them. And this length function here is just saying, like, if this tile is part of a long road, what is the length of that road? And this is all we need. So what I've done is in my little simulation here, I've implemented this as a new wave function. And if I run this, then what we get is exactly the same as before, where we have this middle starting tile, and then these possibilities around it.
But it's favouring the two at the side.
Yeah, exactly. These have a lower entropy, and I'll show you why in a second they have a lower entropy. But we're favouring them because they are now going to continue this road, right? Whereas this one in the bottom is going to be a new road, and so it's kind of weighted less. And so I can take the next option, and it's going to do that for me. So here, we don't have a road to append one. So actually, these are all kind of equally as bad, you could say. And again, wow, we're not getting many roads here. Okay, and now we have an end of a road. So equally, it's going to put it on either end. And this is a key thing, is it's not going to care if we're ending a road, right? But you could totally imagine defining another wave function which also tries not to end roads if possible. So you could do these sorts of things. But if I just run this and let it finish, we get kind of similar to before. We have a few holes, but we have much longer roads and much fewer kind of incomplete roads, right? So why is this choosing the cell which would give us the longest road? Because we've only redefined the wave function. But if you remember, it's the entropy that actually determines which cell we choose to collapse. And the entropy, I previously said, is just the length or the amount of possibilities we have, right? But I'm going to redefine this to something a little bit more complicated, but a little bit more real, which is something called Shannon entropy. I think Computerphile has covered this before on a video, I believe. There's a little bit of maths, but it's not much, and the intuition is easy. So what I'm going to write is the entropy of some cell, rather than just being the length of possibilities, it's actually going to be minus the sum of p times log p. And p here is the probability, essentially the weight of each possibility, right? So in our example here at the top, we have a 2 and a 5. These are not probabilities. I'm going to have to actually normalize them. So this is going to give me minus, so that's, the first p is going to be 2 over 7, which is the total. 2 over 7 times log 2 over 7, plus, because this is a sum, plus 5 over 7 times log 5 over 7. The intuition here is that it doesn't really matter what log is doing here. It doesn't really matter what anything is doing here. All you need to think is that this entropy gives you the property that if we have just one option, so just one option here, this is going to be 0. Let's say we have 2 options, but they're equally likely. This is going to be something. This actually happens to be about 0.7, but whatever. But if we have 2 options and like one is a lot more likely than the other, this is going to have a lower entropy than this. This is going to be something about 0.3. So intuitively, you just want to think the entropy is now measuring how surprising would the answer be if we find out. If we find out, given one option, the answer is that option, it's not at all surprising, is kind of the base case, right? And what this does is that now, when I've redefined my wave function to give me these really big numbers, if I have really big really big roads, then that's going to give me a lower entropy in these cases because you can sort of think it's less surprising to choose that one. It's just number crunching really behind the scenes. But we get exactly this behavior that we wanted. And actually, we can apply the exact same logic to cities as well. You could imagine this one. You could imagine that we have this road wave function with an R next to it. You could define exactly the same thing for cities and just measure the length of all the cities. And in fact, I've done that, and we get a really cool behavior, and I think quite a natural thing. It almost looks like humans playing it, right? So again, this sort of, the brighter green is saying this is lower entropy, so it's more likely to be chosen. And so here we have a road, but it actually also has a city, so that's interesting. And this is interesting because what I've done is now I've composed two wave functions, and I've composed the city wave function and the road wave function. And I've composed them in such a way that the city one takes priority. And you can see this here. I could have placed this next to an existing road and made a road of length 2, but I've chosen to place it next to a city. I made a city of length 2. But now I just have a road, so I have to put that next to a road. And I can go on and go on and go on. And this, I think, is a really nice result. We have lots of connected roads. We have some nice big cities. This would score quite high in the game. We now have something which is arguably quite close to maybe how humans would play this, depending on the humans. And well, the whole reason really why I was quite interested in doing this project to start with was I just wanted to see a really big Carcassonne map. I always think this when I play it, like, what does it look like if you have like 10 decks and you just sit there for hours playing? So we can simulate that. So I'm gonna make myself an infinite number of decks. Let's have a bit of a larger board as well to play on and set it going, I suppose. So here we're gonna start off with the tiny little cell in the middle, and I can just run it. And I think at this scale, it's easier to sort of see what's going on because it's a little bit slower. We really are, you can see it in real time. We're prioritizing these long roads and these large cities, and it's really fun to watch.
It reminds me of when I used to play kind of sim games and you would speed the time
up. Exactly that.
Before unleashing the monsters.
Exactly that. And actually, looking at this really reminds me of L systems as well. I think that there's a link here. I haven't been able to quite put it into words, but I think that there's an interesting link between the two systems. I'm going to put my code, well, it's already on GitHub, actually. It's totally public. We'll put the link in the description. Feel free to check it out. I would really recommend kind of going in and defining your own wave function and defining your own entropy function and see, like, what kind of stuff can you get? Because another really interesting thing you can play around with is rather than always collapsing the minimum entropy cell, you could collapse, for example, the maximum entropy cell, and then you get some really
avoid roads and avoid, yeah.
Yeah, and you can get some really interesting behavior like that. Play around with it. It's written in a way that you should be able to. Not too difficult. So yeah, in the background here we have the same thing, but now rather than choosing the minimum entropy to collapse first, we're choosing the maximum, and we get this kind of like tendrily.
Oh, because it's avoiding.
It's sort of avoiding things.
Avoiding cities, and it's okay.
The super cool thing is actually that
it's like a circuit board.
It looks good, doesn't it? And but also all of these pockets are like very nearly determined, right? So it sort of thinks it knows, but then it just kind of like it saves them to later, right? Until it actually needs to fill in. Anyway. I digress. I think I should probably leave it there, but yeah, just to conclude, really, I still think that procedural generation and this sort of like really complex behavior from easy to define, easy to write down rules, I just think it's such a fun thing, and I guess that's the main point I wanted to make, is that I just really encourage you to play around with these things and write your own code to do this, or simulate some other kind of physics things, or whatever it might be. just to say also, all of the images in this simulation here are generated by the user MLIN92 on Wikipedia, so thank you very much for that. But yes, go and try it out, and like, yeah, this algorithm is really cool.